In this video, we're going to take a look at the rectangular coordinate system and graphs. So the rectangular coordinate system is also called the Cartesian coordinate system or the Cartesian coordinate plane. What we have is two number lines laid out. One is the x-axis, which is the horizontal axis, typically, and another is called the y-axis, which is typically the vertically aligned axis. Now, in order to plot a point in the Cartesian coordinate system, we move in the x direction and move in the y direction. The x direction, we move left and right. The y direction, we move up and down. And so each point is going to be an ordered pair, x comma y. Now, one special point is the origin. That's the point 0, 0. When we graph any other point, we start typically at the origin and graph from there. Another thing about this rectangular coordinate system or Cartesian coordinate system is that it naturally splits into 4 quadrants. Here we have those quadrants labeled. Quadrant 1 is in the upper right-hand side. Quadrant 2 is in the upper left-hand side. Quadrant 3 is in the lower left, and quadrant 4 is in the lower right. And what we typically do is we think of it as starting at quadrant 1, and then 2, 3, and 4 are labeled that way by moving counterclockwise. Now, just as a point of emphasis, all points in quadrant 1 are going to have positive x values and positive y values, because when we move in the x direction, moving to the right gives us positive numbers. When we move in the y direction, moving up gives us positive numbers. So positive x's mean I've moved to the right. Positive y values means I've moved up. Notice that quadrant 2, you'd have a negative x value because you'd move to the left, but you'd have a positive y value because you moved up. Quadrant 3 is negative, negative. You move negative in the x direction and then negative in the y direction. Quadrant 4 is positive in the x direction, but negative in the y direction. Now, you might ask, what if a point is on the axis? For instance, what about the origin? Or what about another point that's on the axis? Well, points on an axis are technically not in a quadrant. And that means they'd have a 0 value as their x value or as their y value. But points on an axis are not in a quadrant, and those will have a 0 in the x position or a 0 in the y position. So let's go ahead and plot some points on the rectangular coordinate system. And when we do that, we'll also state which quadrant the points are in. Here are 4 points, 3, 4, 3, negative 4, negative 5, 2, 9, 5, and negative 2, negative 8. Let's go ahead and plot these on the rectangular coordinate system. Now I have Desmos pulled up and it has a nice built-in rectangular coordinate system grid already on it. You can use other grids as well. But I'm going to plot on this. The first point is 3, negative 4. That's a positive 3 in the x direction, and then a negative 4 in the y direction. So we get this point right here. Oh, let me redraw that. That point right there, 3, -4. Oh, let me draw that a little bit nicer. And I'll emphasize where it's at. So there it is, 3, -4. That's the point we were asked to graph as the first point. -5, +2 was the next point. That's going to be -5 in the x direction, +2 in the y direction. That's going to be over here. And notice, by the way, 3, -4, that's in quadrant 4. -5, 2, that's in quadrant 2. Now 9, 5 is the next point we're asked to plot. 9, 5 is up here. 9 in the x direction, 5 in the y direction. And there that is. Again, that's in the first quadrant. We're talking about quadrants. And then -2, -8 means I go -2 in the x direction, -8 in the y direction. So it would be right there. Now that's how you can manually draw it. You just draw a circle or fill in a point, fill in the dot there. If I didn't want to uh, draw that manually, what I could do is on this graph on Desmos, I can actually just plot the points. So 3, -4, exactly where we said it was going to be. And then -5, +2, again, exactly where I said it was going to be. And then 9, 5, again, there's where we said it was going to be. And then lastly, -2, -8, right there where we said it was going to be. So we can plot these directly as well on Desmos using the technology. That's not what our example 1 asks us to do, but it is nonetheless. Let's go ahead and do example 2 as well. Plot these 4 points on the rectangular coordinate system and state what quadrant the point is in, each point is in. Push pause on the video and try this on your own if you'd like, and in a couple of seconds, I'll show you how it's done. All right, so let's go ahead and do this. The first point that we are asked to plot is the point -2, -2. So that's going to be right there in quadrant number 3. The next point is 0, 3. Now 0, 3 means I go 0 in the x direction, so I do not move left or right at all, and I move up 3 units. So 0, 3 is a point on the y-axis. So it's this point along the y-axis. By the way, since it's on the axis, since 0, 3 is on the y-axis, it is not in a quadrant. So we'd say 0, 3 is not in a quadrant. The next point it asks us to graph is -4, 0. That's left 4, and then 0 up and down. So that's going to be on the x-axis. Notice that the point on the y-axis had an x value of 0, and the point on the x-axis had a y value of 0. Again, that's not in a quadrant either. -4, 0 is not in a quadrant. And then lastly, the last point in that example was the point 7, -3. 7 in the x direction, -3 in the y direction leaves us at this point down here. So 7, -3 is right here. Again, the quadrant that point is in is quadrant 4. So quadrant 1, 2, 3, 4. So that quadrant is quadrant 4. If we're on the y-axis or on the x-axis, we are not in a quadrant. So that's the idea of plotting points. So plotting points on the Cartesian coordinate system or the Cartesian coordinate plane, or plotting points on the rectangular coordinate system, rectangular coordinate plane, is an important thing to do. By the way, let me just state this. The reason why we call this the rectangular coordinate plane is because if we're moving to hit points like we did when we went and found point 7, 3, we're moving in rectangular fashion. We're moving left and right and up and down. So when we went to 7, -3, we went right and down. You could have also gone down and to the right. And notice that all of the whole grid is basically in rectangles, squares and rectangles, but a square is a special type of rectangle. So that's why we call it the rectangular coordinate system. The Cartesian coordinate system is actually named after a guy named Descartes, and he's a famous mathematician there. But it's called rectangular coordinate system because you move in rectangles. The directions you move to get to points, your movement is rectangular. Or it's called the Cartesian coordinate system, named after mathematician Descartes. Now, the reason why we focus a lot on the rectangular coordinate system, which is the Cartesian coordinate system, is for equations in two variables. When we have mathematical equations written with two variables, and the default variables are x and y, but you could have any other variables as well, then we can find solutions to those equations. So for example, here's a very straightforward equation, y equals 3x minus 4. A solution to that equation is a point that makes the equation true when I plug in the values for x and values for y. So for instance, if I plug in -1 for x and -7 for y, I get -7 is equal to 3 times -1 minus 4. If I simplify the right-hand side, I end up with -7 is equal to -7. That's obviously true. Therefore, this point is a solution to this equation. On the other hand, if you plug in -1, 2 and do the calculations, you'd end up with 2 equaling -7. That's obviously false. 2 is not the same number as -7. And therefore, this -1, 2 is not a solution. Now, -1, 7, -1, -7 is not the only solution to this equation. In fact, there are a lot of them. And that's what graphing an equation in two variable does. When we want to graph an equation in two variables, it means we want to plot all of the solutions on the rectangular coordinate system. So we're going to be looking at plotting all solutions on a rectangular coordinate system, all solutions to an equation in two variables. So all ordered pairs that make the equation true. Now, there's a number of different ways we can do this. One way is by plotting some points. When we get into specific types of equations, we'll also get into specific ways we can actually graph an equation in a straightforward manner by adjustments. We'll see those later. You can also graph by technology. So those are the two ways we're going to graph equations right now. And again, later on in the class, we'll see some other ways to graph equations in two variables. So let's start by graphing this equation using a method of plotting points. So what most people do is they start out by drawing a table, all right, with X values and then corresponding Y values. And what we're going to do is we're going to plug in just some numbers for X. So maybe I plug in the number -1 for X. Okay. If I plug in -1 for X, what I do is I replace this X with a -1. And that gives me an equation in one variable that I can solve. So this is pretty straightforward because solving this just means simplifying the right-hand side, and I get a -7. And so when I plugged in -1, the corresponding Y value was -7. Now, that is a point that's going to be on the graph. That's a solution to this equation. In fact, it was the solution we saw earlier. And so now I know that the point -1, -7 is on my graph. Then I'll plug in different X values. Let's say we plug in an X value of 0, an X value of 1, an X value of 2, an X value of 3, an X value of, you could plug in anything. In fact, let me plug in 1, I'll do 1.5, and then I'll do 2, and then I'll do 3. Just emphasize you can plug in any numbers you want. They don't always have to be whole numbers, but a lot of times whole numbers are a little bit nicer. Or integers are nice in the case like -1. So if I do plug in a 0, what my corresponding Y value will be is a -4. 3 times 0 minus 4 gives me a -4. So my corresponding Y value is -4. That means the point 0, -4 is on the graph. You can do this for any value of X. So I plug in a 1, 3 times +1 minus 4 is a -1. So I get 1, -1 as a point on the graph. When you plug in 1.5, 3 times 1.5 minus 4 gives you a positive 0.5, or just or sometimes you just write 0.5. So that's another point on the graph. What if I plug in the number 2 for X? 3 times 2 minus 4. That's 6 minus 4, which is 2. So that tells me the point 2, 2 is on the graph. Well, if I plug in a 3, 3 times 3 minus 4 gives me a 5. So that tells me the point 35 is also on the graph. Now, you could keep doing this as much as you want. You can plug in lots and lots and lots of x values if you'd like. But for right now, we hope that if we plot all of these points, we can see a pattern. So what I'm going to do is I'm going to take all of these points and I'm going to plot those on the Cartesian coordinate plane and see what the pattern is. Now, I've already done that. Excuse me. I've already done that, and we've gotten these 6 points. So here's the list of all those points. I've put them all in black, and you can see what's happening here is that the pattern is a straight line. And so if I were to graph this, I would connect, whoops, I would connect all of those dots and then extend that pattern on forever. Again, oh, I didn't draw that very good. I'd extend that pattern on forever by putting arrows on the side. Now, if you do this in on Desmos, you can actually just write out y equals 3x minus 4, and it'll give you a nice straight line. Obviously, when I drew it on the screen, it wasn't nearly as straight as it could have been. But what we're saying is that every point on this line, every point, for instance, like -2, -10 looks to be on that line, that is a point on that will be a solution to the equation in two variables, to the equation y equals 3x minus 4. So every single point on this line, and if you zoom out, you'll see that this pattern goes on forever. And so that's how we graph an equation. We plot some points, we see the pattern, and then we connect those points and then extend that pattern out forever. Now, when we get to general graphing, there'll be some intricacies that we'll have to be careful of when we're plotting points and extending patterns. But for right now, we can just do that. So let's do example 4 as well. I want you to graph this equation using a method of plotting points. The equation is y equals -x plus 2. Push pause on the video. In a couple of seconds, I will show you how this is done. All right, so I'll do this one. Y equals -1x plus 2. By the way, that can also be written as y equals -x plus 2. I think the values of x that I'll plug in are going to be -2, -1, 0, +1, and +2. I like plugging in fairly small values of x if I'm plotting by hand. If I plugged in an x value that was like 37, that wouldn't help me as much unless I have a really zoomed out graph. And most of the time when you're graphing by hand, you have like a graph that might go from -10 to +10 in the X's and Y's. So now we're ready to plug things in. If I take -1 times a -2 plus 2, I'm going to get a +2 plus 2, which is a 4. So we're going to get y equals 4 there. If I plug in an x value of -1, -1 times -1 plus 2 gives me a y value of 3. If I plug in the number 0, I get a +2. If I plug in the number 1, I get a +1. -1 times +1 plus 2, so that's -1 plus 2 gives me +1. And then if I plugged in a 2, I get a y value of 0. I'm not going to write the points. I don't need to do that now. I think we all understand. Here we have the point -2, 4, -1, 3, 0, 2, 1, 1, and 2, 0. So we could plot each of those 5 points, and hopefully that gives us a pattern that we can recognize on the graph. So here are those 5 points: -2, 4, -1, 3, 0, 2, 1, 1, and 2, 0. Notice that we have this pattern. It's a straight line moving down and to the right. And if I connect those dots and extend out, I'm going to not do it by hand because I'll be a little bit too wobbly on the screen. But if we connect those dots and extend out, we get this line. So this is the graph of y equals -1x plus 2. Here's another equation where we have y equals x squared minus 1. And it asks us to graph this equation by plotting some points. If you want to try this on your own, push pause on the video and plot some points. This one you should not get a line for. In a couple of seconds, I'll show you how this is done. All right, for this one, I'm going to put in a few more points than I did for the previous two because this one has an x squared in it. So I'll plug in -3, -2, -1, 0, 1, 2, and 3 for x, and then solve for y. So if I plug in a -3 for x, I'll plug in -3 and then square that and then subtract 1. Be careful of where you place your parentheses here because the -3 is -3 times another -3. It's x times x. Therefore, it's going to give me a +9 minus 1, which is an 8. So my y value is an 8 when I plug in a -3. Now, let me just point out something. If I would have plugged in a +3, since 3 times 3 is 9 as well, my y value would have been 8 if my x value were a +3. Let's move on to the -2. Plug in a -2. -2 squared is a +4. Minus 1 is a 3. Whoops. So we end up with -2 3. And if I would have deleted the negative, if I would just plugged in a positive 2, I would have also gotten 4 minus 1, which is a 3. If I would have plugged in a negative 1 squared is positive 1, minus 1 gives me 0. That would have been the same as if I would have plugged in a positive 1 as well. So my y value is 0. When the x value is negative 1, my y value is 0 when the x value is a positive 1. Now the last x value that I'm going to plug in is a 0. 0 squared minus 1 is negative 1. So that gives me the point 0, comma, negative 1, a point which has x value 0 and y value negative 1. Let's go ahead and plot these points on my graph. Now, I've already plotted these points. So negative 3, 8 is right here. Negative 2, 3 is here. Negative 1, 0, then 0, negative 1, then 1, 0, then 2, 3, and then 3, 8. So you get this pattern where left to right, you're traveling down and you're hitting this sort of bottom point and then coming back up. So you'd connect the dots, and when doing so, you'd connect them in a smooth way. So you'd kind of round out this bottom. And like I said, I don't like to draw this because usually my drawings are not very good when I'm drawing on the screen. So I'm just going to let Desmos draw it in a smooth way. And here's how it looks. So that would be the graph of y equals x squared minus 1. Obviously, this is not a straight line. This figure is called a parabola, and we'll look more at parabolas later on in the course. Now, obviously, we did those last three examples by plotting points. We could have also graphed these using technology. And obviously, I've kind of used Desmos on all three of these, so I'll use that again. But I will say the TI-84 can graph these really nice. Any graphing calculator will graph these three equations really nicely as well. So with Desmos, all you have to do is you have to just type in the equation into Desmos, and it will give you the graph. So for instance, here's y equals 3x minus 4. And if you hover your cursor and clicked the click on the left button there, left click on this, you can actually scroll through points and highlight certain points. So here I've highlighted the point negative 1, negative 7 on y equals 3x minus 4. Here's the point 0, negative 4. Here's the point 3, 5. Well, if I can get there. Sometimes it's hard. 3, 5. Again, if we wanted to do that same thing with y equals negative 1x plus 2, I can do that. So here's the point negative 2, 4. And then again, just highlights various points as I scroll around. The TI-84 calculator can also highlight points using the trace feature. And I will put up a basic graphing video on the TI-84 for anyone who's interested in that as an addition to this video. Now, y equals x squared minus 1. Again, I just have to type that in to my equation. The caret key does the exponent, and I get this. Look, again, if I left click, it'll highlight points on there. In fact, it'll highlight lots of points. So there you go. That's how you can graph with technology. Again, I'll put an additional video to graph using the TI-84 up in addition to this one. Now, I want to make a note on the three equations that we did in examples 3, 4, and 5. These equations were both really nice to plot points on and really nice to graph using technology because all of them had the form y is equal to an expression in x. So we had y equals 3x minus 4, y equals negative 1x plus 2, y equals x squared minus 1. We always had y equals. So it was really easy to plug in x values and find the corresponding y values. It was also easy to plug those in to a calculator, to a graphing calculator, when we have an equation like that. When I have y is equal to an expression in x, it's really easy to plug in that into the calculator. But not all equations that we're going to see in this class will look like that. We'll look at some other equations later on, not in this video, but we'll look at some other equations that maybe don't have that form, and we'll do those later. But that's just a note. Just figure out. Now, there are some important points on graphs, and there's certain points that are named. Two important points on graphs are the x-intercepts and the y-intercepts. Two different kinds of important points on graphs are the x-intercepts and the y-intercepts. An x-intercept is where the graph hits the x-axis. Now, if it hits the x-axis, it's going to have, the point will have the form x comma 0, because all of points of that form are the points on the x-axis. If it had a different y value other than 0, then it would not be on the x-axis. The other important points are the are the y-intercept. A y-intercept is where the graph hits the y-axis, and it has the form 0 comma y. And equations can sometimes have multiple x-intercepts, they can have multiple y-intercepts, or they might have just one x-intercept or one y-intercept, or sometimes 0 x-intercepts and 0 y-intercepts. It kind of depends on what the equation looks like. In order to find an x-intercept, since it has the form x comma 0, all we have to do algebraically to find an x-intercept is plug in a y value of 0 and figure out what values of x would work. That's just the opposite if we're trying to find the y-intercept. If we're trying to find the y-intercept, since the y-intercept has the form 0 comma y, We just need to plug in an x value of 0 and solve for y. By the way, this is not just for equations like we've dealt with before. This is for all equations that we're going to have in x and y. If we want to find the x-intercept, plug in y equals 0. If we want to find the y-intercept, plug in 0 for x. So let's algebraically find the x and y intercepts of this equation without graphing. So algebraically, we'll do it. Y equals 3x minus 4. Obviously, we've dealt with that equation before, so it should be something that's very familiar to us. All right, so let's go ahead and do this. I left the table up from what we did earlier. But the y-intercept, remember to find the y-intercept, we plug in a 0 for x. So we're going to get y equals 3 times 0 minus 4. And that is a y of negative 4. Now, some people would call the y-intercept the value negative 4. But specifically in this class, I always say the y-intercept is the point 0, comma, negative 4. The y-intercept is the point where our graph hits the y-axis. So in this case, that's 0, negative 4. By the way, we could have also looked on our table to see that as well. The x-intercept we get when we plug in 0 for y. Now that's going to be 0 is equal to 3x minus 4. And that's going to cause me to have to solve this equation. I'll solve that in this case. In this case, I'd have to add 4 to both sides and then divide by 3. So we get 4/3 or 1.33 repeating as my x value. So my x-intercept, where my graph hits the x-axis, is at the point 4/3, comma, 0. So that is how we find the y-intercept and the x-intercept. Let's go ahead and find the x and y intercepts of the other two equations we looked at earlier. Let's do y equals negative 1x plus 2, and we'll find the x and y intercepts of that equation. And then we'll find the x and y intercepts of the equation y equals x squared minus 1. Go ahead and try to do these on your own. Push pause on the video, and in a couple of seconds, I will show you how that is done. Let's look at doing these two problems. I'll first find the y-intercept in example 7, y equals negative 1x plus 2. In order to find the y-intercept, I'm going to plug in 0 for x. That's y equals negative 1 times 0 plus 2, which is a y equals 2. And I get the y-intercept of 0, 2. So that's the point at which this y equals negative 1x plus 2 hits the y-axis. For the x-intercept, I plug in a 0 for the y value. In this case, I get negative 1x plus 2 is equal to 0. I would subtract 2 from both sides and then divide by -1. If I divide it by -1, I'll get x is equal to a +2. So I get 0, 2, and 2, 0 as my y-intercept and my x-intercept respectively. Notice that both of those we had seen when we plotted points. Now, these two examples were both lines, straight lines. So there was only one place where we crossed the y-axis and one place where we crossed the x-axis. With the parabola that we had graphed, that was not the case. So if I were to find the y-intercept of y equals x squared minus 1, I'd plug in 0 in for the x. When I square it and subtract 1, I get a y value of -1. So the y-intercept is the point 0, -1. Now, if I'm trying to find the x-intercept, I'd plug in a 0 for y. I would get x squared minus 1. And when we add 1 to both sides, we'd get 1 is equal to x squared. Now, there's actually two different numbers when you square them that give you 1. Obviously, 1 squared is 1, but also -1 squared is 1. So here we actually have two x-intercepts. One is the point, whoops, 1, 0, and the other is the point -1, 0. So two x-intercepts in this on this graph, two places where this graph hits the x-axis. And if we looked at our graph, we could confirm that. Let's go ahead and look at the graphs of examples 6, 7, and 8. We had already graphed these earlier, so might as well take a look. Sure enough, when we have y equals 3x minus 4, you can see that we cross the y-axis at the point 0, -4. We cross the x-axis at 1.3 repeating, comma 0. 4/3 is the fraction version of 1.3 repeating. So we see we do get the correct answers. Here I'm graphing with Desmos, but you can just as easily graph with the graphing calculator as well. When I take y equals -1x plus 2, 0, 2, and 2, 0, 0, 2 is my y-intercept, 2, 0 is my x-intercept. So we get a single y-intercept and a single x-intercept in that case as well. Straight lines, you can see, are going to, generally speaking, pass through the y-axis just once, pass through the x-axis just once. And then lastly, we had this parabola, y equals x squared minus 1, and we can see that there are two different places where the graph crosses the x-axis. That was at -1, 0 and 1, 0, just like we said. And then the place it crosses the y-axis is at 0, -1, just like we found out algebraically. So all three of these examples matched up with what we had graphed earlier. Now, I want to again state something about x and y intercepts. In some equations, it's harder to find x-intercepts and harder to find y-intercepts than the examples that we just went over. We went over fairly straightforward examples where the x-intercepts and the y-intercepts were straightforward and easy to find. But not all equations will that be true for. And like I stated earlier, some equations might not have an x-intercept, and some equations might not have a y-intercept. Some will have an x-intercept and not a y-intercept. Some may have a y-intercept and not an x-intercept. So don't just think we're always going to have to find an x and y-intercept and they're always going to be really easy to find. Sometimes they're a little bit trickier. Now, we found x and y intercepts primarily by using algebraic methods earlier. We can also find x and y intercepts by graphing. So what if we graphed y equals x squared minus 3x minus 10? You can graph this on Desmos or on a TI-84 calculator. Again, there'll be an additional video paired with this one for use of the TI-84 calculator and basic graphing. But for this present video, we'll just use Desmos. So we'll just use Desmos. And again, all I have to do is I have to click in this slot and type in y equals x squared minus 3x minus 10. And I get this graph. Now, doesn't look really fantastic now, but you can zoom out or zoom in as much as you want. And if we're looking graphically for my y-intercept, it's down here at the point 0, comma, negative 10. So 0, negative 10 is my y-intercept. That's where the graph crosses over the y-axis. So that's the y-intercept. And you can see we have two x-intercepts, two places where our graph crosses the x-axis. And graphically, visually, we can see that that happens at the point negative 2, 0 and at the point 5, 0. So this equation has one y-intercept and two x-intercepts. The y-intercept is 0, negative 10. The x-intercepts are negative 2, 0 and 5, 0. Let's do one more, finding the x and y-intercepts of the equation by graphing. Here we have y equals negative x squared minus 3. We could plot points and graph this and see what's going on. We could use some other methods, but for this, I'm just going to graph this in Desmos. Again, if you want to graph in the TI-84 calculator, then that would be great too. Again, another video will show you how to do that. So once again, I just take a blank spot and I type in y equals negative x squared and then plus 3. Y equals negative x, minus 3, excuse me. Y equals negative x squared minus 3. We can see that this graph hits the y-axis at the point 0, negative 3. So that's the y-intercept. but this graph never gets high enough to touch the x-axis. So this is one of those examples where we have a y-intercept, but we do not have any x-intercepts. So there's no x-intercept with this one. Later on in this class, we'll see how to actually see that algebraically rather than by just graphing. But here, one y-intercept, no x-intercepts. So that's the basics of the rectangular coordinate system and graphs in two variables on the rectangular coordinate system.